Hello everyone, today we're going to talk about kinetics, specifically rate expressions. Now if you look at the top of your screen, you will see a balanced equation. Now this is the same balanced equation you've been looking at since Gen Chem Round 1, the only difference is now very generic. If you look one equation down, you will have a very generic rate expression equation, rate expression. This lets us figure out the relative reaction rate for the entire reactions and individual reaction rates for both the products and the reactants. And these two are interconnected. Now let's take a look at the left side of the arrow. To the left you have your reactants, and those experience a rate of decomposition. And the reactants during a reaction decompose. They break down into the products. If you look to the right side of the arrow, we have our products, and those undergo a rate of formation. As the reactants break down, the products are formed. So as your reactant concentration decreases, your product concentration increases. And this equation here is closely linked with this one. If you look at the coefficients out in front for the balanced equation, you have A, B, C, and D. These are found in your rate expression. Now it's 1 over the coefficient. 1 over A, 1 over B, 1 over C, and 1 over D. The only difference for the reactants is that you have a negative sign, and that is a very useful negative sign. When we have a change in anything, you have final minus initial, and that can be change for absolutely anything. With your reactants, they're decreasing, so you'll have a smaller final than you did initial. If you started with, let's say, a concentration of 1 molarity of anything, and after a certain period of time you had 0.6. If you take the difference of these two things, you're going to get negative 0.4 molarity. This negative here cancels out with this negative over here, leaving a positive product and giving us a positive overall relative reaction rate. And this is very useful. Now, to the right side of the arrow, down here, you will see that for the products, everything is positive. If you need a way to think of it as positive products. Match up the P's so you can remember which sign goes where. If the products are positive, that means the reactants must be negative. Now I'm going to scroll down and we can put this into practice. Here it says consider this redox reaction. The redox part of this isn't particularly important for what we're doing. So take a look at this lovely balanced equation, then look at what we're being asked. If we're told that the change for Br2, a product, is 0.03 molarity per second, what is the change in Br1, a reactant, over time? The first thing you're going to do after identifying what's a product and what's a reactant is to write a very kind of generic rate expression. Here for Br2, we see that the coefficient out in front is a 3, and because it's a product, it's positive. So you're going to have 1 over 3. And that is going to be times the change in Br2 over time. Same as we had like change in delta C over time over delta T, same thing, just plug it in. So that's going to be 0.03 molarity per second, and that is going to equal the reactant that they want us to find. Now because this is a reactant, it needs to be negative. So you need to have a negative 1 over the coefficient, which is 5. Negative 1 over 5. Now for the brackets, you have two options of what you can put in here. You can put in this, or you can just write x. Personally, I think writing x makes things easier. And now it just looks like high school algebra. When you're solving for x, take this negative sign with you. we need to have a negative answer for x. Now if you rewrite this, you end up with negative 5 over 1 times 1 over 3 times 0.03 molarity over seconds equals our x. If you do the math, you end up with negative 0.05 molarity per second equals x. And that's our individual reaction rate. And if you look back, this makes sense. We had a reactant, so that's going to be decreasing. And here we have a negative answer. So that will be decreasing, or shows that it decreases. And the fun part about this is you can prove that you did this right. You just plug in for x with what we just found. So we found that x equals negative 0.05 molarity per second. That's what we solved for. Now take a second to erase this. Solve for both sides. If we did this correctly, they should be equal to each other. Here, this ends up being 0.01 molarity per second on the left side of the equal sign. To the right, we have negative times a negative. That gives you a positive. And 0.05 molarity per second divided by 5 is 0.01 molarity per second, or molarity per second. This is a true statement. 0.01 molarity per second does equal 0.01 molarity per second. And that is how we solved for Br minus. And there you go. That is how you solve for rate reaction or rate expressions. I hope this helped, and if you have any questions, please let me know. I'll see you in class.